All right, we're going to keep going with exponential functions, and here we have a challenge in a real-world connection problem. I encourage you to pause this video and try these on your own first, and then check back in and see how you did. So the first one, the challenge problem, we want to solve for x. And it says we can use Desmos for it, okay? I want to do a little bit of work by hand first, but this is actually an example, maybe the first one you've seen, of the exponent being the unknown that we need to solve for. And we don't have any great tools to do that right now. In Algebra 2, you'll learn logarithms, which will help you solve for these with a regular old scientific calculator. But for now, we need to use Desmos to solve. So one thing I can do right away is I can just divide by 2.5 right away. And so that's a valid thing I could do pretty easily. And 31 over 2.5 is 12.4 equals 1.15 to the x. By the way, what this might model in the real world, it's the numbers are going to be goofy with this example I'm going to describe, but go with it. Let's say you have $2.50, so that's 2.5, and you're investing it in a bank account, and the bank account pays you 15% interest. Okay, so that's the decimal above and beyond the 1 that is in our base here. So the 0.15 means we're getting 15% interest. And we're wondering how many years, that's x, how many years it'll take to get $31 in our bank account. This could work for $2.5 million with 15% interest. How many years would it take you to get $31 million, right? But anyway, let's keep going. We're going to solve for x. And now we can do a little bit of guess and check to just kind of get in the ballpark. What's 1.5 to the 10th? What's 1.15? 1.15 to the 20th, 1.15 to the 30th. And let's see what those guys are. So could it take 10 years? That would give us 4.05, so we would need more years than that. Could it take 20 years? That would get us 16.37. So we don't even need to try the 30 years, right? It's somewhere in there between 10 and 20. Let's try 15 years. 1.15 raised to the 15 is 8.14. So my guess is it's going to take maybe 17 or 18 years in that money example, or just x should be about 17, 18, 19, somewhere in there. So what we're going to do is we're going to go to Desmos, and we're going to type this into Desmos, but not exactly that. We're going to type it in as two separate equations. This is going to be one equation, and this is going to be the second equation, and we're going to look for where they intersect. So my red equation will just be a horizontal line at 12.4, and my purple equation will be an exponential function. So let's go ahead and do Desmos here, 12.4 and 1.15. So our first one is just y equals 12.4, and that's, like I said, a horizontal line right there. And our second equation is y equals 1.15 to the x. Okay, and so we can see that exponential growth happening right there. And it looks like we have an answer, and 18.014 is when y becomes 12.4. So let's go ahead, and 18.01, we can go back. So it looks like x equals 18.01. So a great way to check it, which is probably a good thing to do here, is to just plug things back in. So is 31, is that equal to 2.5 times 1.15 to the 18.01? And let's see what we get. And we get, is this equal to 30.98? It is. It's within the world of rounding. So we rounded that 18.01 a little bit. So looks like we did it correctly. So x is 18.01 right there. All right, next one. Let's see, a real-world connection problem. By the way, if I encourage you to search for this on YouTube, look for Al Bartlett's exponential growth videos. And they're really old school. They look like they were made in the 70s or something, but they are just fascinating. And I encourage you to watch his series on that, or maybe it's an hour-long lecture on exponential growth. Really, really fascinating. So check that out. But here we have bacteria in a flask double in population each hour. And when I started measuring, there were 12 bacteria. Assuming the pattern can continue indefinitely, how many bacteria will there be 1 day later? So one thing we have to keep in mind is we're dealing with different time units, right? So we need to make sure we have a consistent time unit. But let's go ahead and get it started. So we're wondering, let's see, we have an exponential growth pattern. And so this will be time, kind of informally defining our variables here, and that will be number of bacteria. So we can write this out as y equals 12 as our starting amount. Things are doubling each hour, and we're wondering how many bacteria we'll have after 24 hours. I bet we're going to have a lot. Let's run through our calculator and see. 2 to the 24th times 12. So that equals 201,326,592. So 201 million bacteria, and presumably they had enough nutrients and resources to be able to continue to grow to that size, which probably isn't totally realistic, but dang, that's a lot of bacteria right there. All right, that's a good place to stop.